Mhm.
Hi, everyone. Good to see you all. So today we have Martin Dolezal, and he's speaking on descriptive complexity of Banach spaces. So let's go ahead and start, Martin.
Yeah, so first of all, I would like to thank you for the opportunity to have this talk. I will introduce a new natural way how to code separable Banach spaces, and then I will use this coding to examine some isomorphism and isometry classes of certain classical separable Banach spaces. And it is a joint work with three co-authors, Marek Cud, Michal Doucha, and Ondřej Kurka. And I will try to keep my talk as much elementary as possible, so I will not go into the details of the proofs, but I will at least try to explain some of the main ideas of some of the proofs. So first of all, some notation. So whenever you see the acronym SBS, that stands for a separable Banach space, or SBSS, separable Banach spaces. So this is just to make the slides a little bit shorter. So what is a coding of separable Banach spaces? So the class of separable Banach spaces is a proper class, so it is not a set. So we would like to find some set such that every element of the set is a code of some separable Banach space, because then we can use some tools which cannot be used for proper classes. And we would also like to have some additional structure on the set of the codes. So we would like to be it either a Polish space or a standard Borel space. So let me just recall that Polish space is a topological space such that the topology is completely metrizable and separable. And a standard Borel space is a measurable space, which is obtained from a Polish space by taking the sigma algebra generated by the Polish topology. So the only catch is that the Polish topology of standard Borel space is not canonical. So there are many choices of this Polish topology, but we know that there is at least one such Polish topology. Actually, there are many such topologies. Okay, and so why this is useful to have such a coding? So for example, suppose that we have some property P for separable Banach spaces, and we would like to examine the class of separable Banach spaces which have this property. Yeah, but okay, so this is a class, but instead of this class, we may talk about the set of the corresponding codes of the codes of Banach spaces which have this property, and then we may investigate the complexity of this set. So in case of Polish spaces, we may ask whether this set is open or G delta or anything like that. And in case of standard Borel spaces, we may ask if the set is Borel or analytic, and so on. So this is the reason, and let me just show you one example why this may be useful. This is, I would say, a classical theorem today, that there is no reflexive space which would contain an isomorphic copy of every other reflexive space. Okay, we would call such a space isomorphically universal for all reflexive separable Banach spaces. And of course, there are such universal spaces, but none of them is reflexive. And so it was first proved by Schlenk by totally different means, but I will show you the proof by Bossard, which uses a certain coding of separable Banach spaces, which I will introduce in a minute. And so there is one easy fact that the set of codes of all subspaces of some fixed space is always an analytic set. And moreover, Bossard proved that the set of codes of all reflexive spaces is not analytic. And this already implies the result, because if there was a reflexive universal space for all reflexive spaces, then the set of codes of all its subspaces would be analytic by the first fact, but also not analytic by the second fact. So that is not possible. Yes, so this is just an example why this coding may be useful and why it may be useful to investigate the complexities of certain classes of separable Banach spaces. So now I will explain the classical coding, which is the one which is usually considered in literature, which is a coding by a standard Borel space. So we start with some isometrically universal separable Banach space. So for example, with the space of continuous functions on the unit interval, but we could take any other isometrically universal space as well. And we consider the hyperspace of all closed subsets of this set of this space. This is the FC01. And this can be equipped with so-called F-Borel structure, which is a sigma algebra, and it is generated by all sets of this form. So we require that these sets are all measurable. That is, we fix some open set U, and then we consider the set of all those closed subsets of C01 which intersect U. And these are required to be measurable, and they generate some sigma algebra, which is called the F-Borel structure. And it can be shown that this hyperspace with this sigma algebra is a standard Borel space. That is, that there is some Polish topology, although it is not given. And also we are interested not in closed subsets, but in closed linear subspaces, because we want to code separable Banach spaces. But there is this second fact, which states that the set SB, which stands for separable Banach spaces, of those closed subsets of C01, which are linear, is a Borel subset of the hyperspace. So that means that it is a standard Borel space. Yes, so this is one way, and this is actually the coding which Bossart used in the previous theorem. But as I said, there is no canonical Polish topology, because for example, if you tried to use the Vietorist topology on the hyperspace of closed subsets, then this topology is not separable, so it is certainly not a Polish one. Okay, so then there was a nice paper of Godfroy and Saint-Raymond, who introduced a way how to look at certain Polish topologies which are nice. And these are topologies on the same space, on the hyperspace of all closed subsets of C01, and they are called admissible. And there are two axioms for admissible topologies. So I did not write them down, but well, simply the first axiom states that some nice sets are open, and those are the sets from the previous slide which generate the F-Borel structure. So they are always open in every admissible topology. And there is the second axiom, which states that every open set is still at least a little bit nice. So it means that every open set in any admissible topology can be somehow easily constructed from those generating sets. And okay, so by the definition, every admissible topology is a Polish topology, and the Borel sigma algebra generated by this topology is always the F-Borel structure. This follows almost immediately from the definition. And also the space SB, which was defined only as a standard Borel space on the previous slide, now turns out to be a Polish space, because the set of all linear closed subspaces of C01 is always a G delta set in every admissible topology. And the advantage of this approach is that it does not matter too much on the choice of the admissible topology, what are the Borel complexities of sets, because whenever you have two admissible topologies, then the identity function from one of them to the other is of Baire class 1. So that means that whenever you know that a set is open in one admissible topology, then it is already necessarily F sigma in any other admissible topology. And now I have two examples of admissible topologies so that we know that there exist such topologies. So the first one is something like the Vietoris topology, and the second one is the Weismann topology. So I already told you that the Vietoris topology on the hyperspace of closed subsets of C01 does not work because that this topology is not separable. But we can somehow circumvent this because okay, so C01 is a separable metric space, and so there is some totally bounded compatible metric on this space. So we fix some totally bounded metric on C01, and then we take the metric completion of this space with this metric. So we obtain a metric compact space, and we can consider the hyperspace of closed subsets of this completion. And then the Vietoris topology is a very nice topology. It is a Polish topology. It is even compact, and we can somehow restrict it to the hyperspace of closed subsets of C01, where of course this is not said very precisely because the restriction, it is well, it is cheating because a closed subset of C01 does not need to be closed in the completion. But you can identify every closed subset of C01 with its closure in the completion, and then everything works. So this is one way how to construct an admissible topology. The other way is the Weismann topology, which is the smallest topology such that all these mappings are continuous. So that is, we fix some element f of C01, and then every closed subset of C01 is mapped to the distance of this subset to f. And that again defines an admissible topology. So now I will try to explain our new way how to code separable Banach spaces. So I will probably start with some heuristics before the precise definition. So a Banach space is a pair of a vector space with a norm. But actually all the important information is carried by the norm, because the vector space, at least for infinite dimensional spaces, forget now about finite dimensional, but for infinite dimensional spaces, the vector space is always a vector space with a Hamel basis of cardinality continuum. So every such two vector spaces are homomorphic as vector spaces. So the information is carried only by the norm. So the idea of our coding is that we fix some vector space, and then we code the Banach spaces by the norms on this fixed vector space. As the only catch is that the vector space is very large, and it is not clear how to choose the Polish topology on the space of norms. But actually, it is not necessary to define the norm on this large space, because the norm is continuous. So it suffices to define it on some smaller subspace, which is dense. And if we drop the requirement that this subspace is a vector space over the field of real numbers, and we want it to be only a vector space over the field of rational numbers, then we can actually make this subspace only countable. So this is what we do. So we have this vector space V, which is the vector space over rational numbers of all finitely supported sequences of rational numbers. And we can view this space as a subspace of C0. So the word subspace is not completely precise, because we consider C00 as the vector space over real numbers, while V is a vector space over rational numbers, but of course V is naturally embedded into C00. So these are finite sequences of rational numbers. And then we define P as the set of all pseudonorms on this vector space V. And So we want that every pseudonorm on V is a code of some separable Banach space. So how do we obtain such a separable Banach space? So first of all, in the first step, we extend the pseudonorm mu from the vector space V to the vector space C00, which is already over the field of real numbers. And by this, we obtain a pseudonorm on C00. But we want a norm. So in the second step, we take the quotient, where we identify every two elements such that the norm of the pseudonorm of their difference is 0. So then we obtain a norm on C00. And finally, in the third step, we take the completion, which is a separable Banach space coded by the pseudonorm mu. So this is the definition. And now some easy facts. So the set of all functions on the space V, all real function, is a Polish space. And the set of pseudonorms is clearly a closed subset, so it is also a Polish space. But we can also consider only the set P infinity, which are those pseudonorms which are codes of infinite dimensional separable Banach spaces. And this set is a G delta set. And we can also define the set B, which is also a G delta set, and it will be the set of norms, so not of pseudonorms, but norms, by which we mean that after the first step, after the extension on C00, we obtain a norm on C00. So that is that we can skip the second step because the quotient is not necessary in this case. So this is our way how to code separable Banach spaces, either by pseudonorms or by norms. Well, so I explained how to obtain a separable Banach space from a pseudonorm. So now the other way, we want to show that every separable Banach space has some code. So I will show it only for infinite dimensional spaces. For finite dimensional, everything is easier. And I will find a norm, which is a code for this infinite dimensional space. And actually the proof is very easy. We just fix some sequence of linearly independent vectors in X, which generate the space. This is the sequence F1, F2, and so on. And we want to define the pseudonorm mu on the space V. So here alpha i's are rational numbers and ei's are elements of the canonical basis of C00. And we define the norm by these formulas. So it is defined in such a way that the mapping, which sends the canonical vector EI of the basis of C00 to Fi, is an isometry. Yes, so if we do this, then clearly the space coded by mu is isometric to the space X. Yes, so now we have three ways how to code infinite dimensional separable Banach spaces. So I will not talk about finite dimensional spaces, but everything is possible even for them. Yes, so the first way is SB infinity. I didn't define this yet, but I defined the space SB, which are the closed linear subspaces of C01, and SB infinity are those closed linear subspaces which are infinite dimensional. And this set can be equipped with some admissible topology. The other way how to code infinite dimensional spaces is by infinite dimensional pseudonorms. And finally, we can also code them by norms. And there is this theorem which states that it does not depend much on the choice of the coding because the Borel complexities of all sets are almost the same. So it is a similar statement to that of admissible topologies when I said that the identity function between two admissible topologies is of Baire class 1. So here we have a similar theorem which consists of three parts because we want to close the circle. And every part states that there is some nice reduction, either continuous or of Baire class 1, from one of the coding into another. So first of all, there is a continuous reduction from SB infinity with admissible topology to infinite dimensional pseudonorms. So by a reduction, I mean a mapping such that the spaces generated by the first code and by its image are isometric. Yes, this is what I call reduction. So there is a continuous reduction from SB infinity to infinite dimensional pseudonorms. The second result is that there is a Baire class 1 reduction from infinite dimensional pseudonorms to norms. And finally, there is a Baire class 1 reduction from norms to SB infinity with admissible topology. So actually, we know that the first, well, of course, the first result is optimal because the first reduction is continuous and we cannot hope for anything else. But we also know that the third result is optimal. It is, of course, no surprise because the identity mapping between two admissible topologies is also of Baire class 1. So we also could barely hope for anything more. But actually, we are not sure about the second result. Maybe this can be made continuous. Yeah, we don't know that. Anyway, let me just mention that the third result is really very difficult. It was proved by Ondřej Kurka, and it has some nice ideas, and it is very long. I don't remember precisely, but it is something like 10 pages of text. So the last result is really very difficult. I mean, we could prove by much simpler means that the map is of some lower Baire class, something like Baire class 3, I think, but it is really difficult to find it of Baire class 1, or at least difficult for us. Yeah, so I already told you that we will consider only infinite dimensional spaces, and also I will fix the coding by norms, the coding B from now on. So whenever I will talk about some complexities, that will be with respect to the space of norms. So first of all, there is a very nice relationship of the topology on the space of norms with finite representability of Banach spaces. So let me just recall that a space X is finitely representable in a space Y if and only if every finite dimensional subspace of X has an almost isometric copy in Y. Yeah, and this almost isometric can be made arbitrarily close to an isometry. And in what follows, I will denote by this XB the isometry class of the space X, which means that it is the set of all norms mu which are codes for spaces isometric to X. And there is this fact which states that if we consider the isometry class of some separable Banach space X, and if we take the closure, then it equals to the set of all those norms which are codes for spaces which are finitely representable in X. So this is a nice relationship which we used several times in our paper, and you will also soon see an application of this result. So some more notation. So I already showed you at the previous slide that this denotes the isometric class of the space X. And similarly, this denotes the isomorphism class of the space X. That is the set of all norms which are codes for spaces isomorphic to X. And now these are two very well-known facts. The first fact states that the isomorphism classes are always Borel sets, while the isometry classes are always Borel sets, while the isomorphism classes can be Borel, but not always. In general, they are only analytic. So let me just recall the proofs. So the proof of the first statement is based on a result by Melleray that the relation of linear isometry is Borel bireducible with an orbit equivalence relation. that is an equivalence relation induced by a Borel action of a Polish group. And it is well known that such orbit equivalence relations have Borel equivalence classes. And so it follows that also the isometry classes of separable Banach spaces are Borel sets. Well, the other result is based on some examples. So for example, it was known for some time that the isomorphism class of a Hilbert space is Borel. Also later there were found some other examples which are more difficult, but on the other hand there are also known some spaces for which the isomorphism classes are not Borel, for which they are only analytic, such as the space of continuous function on Cantor space, the space capital LP, or the space C0. Okay, so now I will continue with investigating the complexities of the isomorphism and isometry classes of some classical Banach spaces, and I will start with the most simple space, that is the infinite dimensional separable Hilbert space, small LP. And we prove that it is the unique up to isometry infinite dimensional space whose isometry class is a closed set. So let me just note that the isometry class is never an open set, which follows, for example, from the fact that whenever you have an isometrically universal space, then its isometry class is dense. But okay, it can be closed because it is closed for the space L2. So how can we prove it? So L2 is characterized by the parallelogram law, and this law is clearly a closed condition. And also it suffices to verify this law only on some countable dense subset. So it suffices to verify it on elements of the vector space V. And so this leads to the fact that the isometry class of L2 is a closed set. And now we also want to prove that L2 is the only space with a closed isometry class. So suppose that we have some space X with a closed isometry class. And then we can apply Dvoretzky's theorem, which states that, okay, it implies that L2 is finitely representable in every infinite dimensional Banach space. So in particular, it is finitely representable in X. And now we can use that nice relationship of our topology with finite representability. So recall that the closure of the isometry class of X consists of those norms, which are codes for spaces finitely representable in X. So it definitely contains norms which are codes for L2. But on the other hand, we assume that the isometry class of X is a closed set, so the closure is irrelevant. And so the isometry class contains only spaces isometric to X. So this implies that X must be isometric to L2. Yeah, now we can look at the isomorphism class of the space L2, and we have a similar result, that L2 is the unique space up to isomorphism, such that its isomorphism class is an F sigma set. So again, there are some reasons why an isomorphism class of any space can never be open or closed. So for example, this follows from the fact that every isomorphism class is actually dense. But okay, the next question is whether the isomorphism class can be a G delta set. And we do not know that, but we know that whenever X is not isomorphic to the Gurari space, then its isomorphism class is not G delta. And this is based on bare category theorem, because you will see in a minute that the Gurari space is comeager. It is the typical space. I will show it in a while. Actually, we do not know whether the isomorphism class of the Gurari space is G delta. Maybe it is. but no other space can have G delta isomorphism class. So to the proof of this theorem, that L2 is the unique space with an F sigma isomorphism class. So we use the Quapian's theorem, which characterizes L2 as the unique space which has type 2 and cotype 2. And okay, I will not explain what it means, but it can be easily seen that the definition of type 2 and cotype 2 are F sigma conditions, because there are some existential quantifiers which can be taken only over countable set, and then some closed condition follows. So that means that the property of having type and cotype 2 are both F sigma conditions. And from this, it follows that, that the isomorphism class of L2 is an F sigma set. Yes, but the other implication that L2 is the unique space with this property is a little bit more difficult. So let me only say that it is based on the solution to the homogeneous subspace problem, which states that L2 is the unique space up to isomorphism, which is isomorphic to all its subspaces. So the proof goes something like that. If we start with a space which is not isomorphic to L2, then we can find an infinite dimensional subspace which is not isomorphic to X, and from that we somehow follow well, but it is a little bit technical, so I will not explain this. Yes, so now the Gurari space. So I will recall the definition of this space because it is not as well known as for the other classical Banach spaces. So it is the space with some property, and actually it turns out that such a space is unique up to isometry, and the property is that whenever A is some finite dimensional subspace in a bigger finite dimensional space B, and whenever A is isometrically embedded into the Gurari space, then this isometric embedding can be extended to an embedding of the bigger space B. But okay, we may lose the isometry, but not so much, because the extension can be made arbitrarily close to an isometry. So this is the property which uniquely defines the Gurari space up to isometry. And now the theorem, which I will not prove because it is very technical, but it states that the isometry class of the Gurari space is a dense G delta set. So we can say that the Gurari space is a typical separable Banach space. And actually, as I already mentioned on the previous slides, we do not know what is the precise Borel complexity of the isomorphism class of the Gurari space. Maybe it is G delta, maybe it is not, we don't know. Yeah, so then we studied the isometric class of the space capital LP. So the Hilbert space is already excluded. We know that the isometric class is closed. So suppose that P is not equal to 2. And in that case, the isometric class is a G delta complete set. So it is a G delta set, and G delta complete means that it is something like the most complicated among all G delta sets. Yeah, in particular, it is not an F sigma set. So how do we prove this? So we start from the class of script LP1 plus spaces, which are well, I wrote down the definition here, from which we can somehow verify that the set of chords of script LP1 plus spaces is a G delta set. But there is a very nice characterization by Lindenstrauss and Pelczynski that these are precisely those spaces which are isometric to the spaces capital LP of some measure mu. So that is probably a nicer condition. And there are two prominent examples of script LP1 plus spaces, which are the capital LP and the small LP spaces. So now we found a characterization of the capital LP spaces among all these script LP1 plus spaces. And this characterization states, well, something like that. Whenever I give you an element of the sphere, of the space, then you can somehow decompose this element into two elements, which are almost equivalent to the canonical basis of the two-dimensional LP space. Yes, and okay, so let me just explain how you can decompose an element of the capital LP space. So an element of capital LP space is a function on the unit interval, and you can somehow divide the interval into two parts. And you can do it in such a way that if you restrict the function on each of the parts, then you obtain two functions of the same capital LP norm. And this is the decomposition which works for capital LP spaces. And it turns out that capital LP spaces are the only script LP1 plus spaces with this property. Well, anyway, this condition, which characterizes capital LP spaces, is again a G delta condition. And so it follows that the isometry class of capital LP is G delta. Well, the fact that it is G delta complete is again based on some argument based on bare category theorem. So we already know that the isometry class is G delta. And we also find some set in which it is dense, and then we somehow use the bare category theorem, from which it follows that the set is not F sigma. So next we have a characterization. We have computed the complexity of the isometry class of small LP spaces. So we proved that this isometry class is F sigma delta complete. So the proof is similar. Again, we started from the script LP1 plus spaces, which we already know that form a G delta set. And then we found a characterization of small LP spaces, which is somehow of a similar vein as the previous one. But now it is something like that. Whenever you give me an element of the sphere, then I can find such a large natural number n that you are not able to decompose X into n other elements, which would be almost equivalent to the canonical basis of n-dimensional small LP space. Yes, so this time the decomposition is not possible for some large n. And well, of course, so this requires some work, but the idea is that an element of small LP space is a convergent sequence. So I can always find a very, very big natural number n, such that if you decompose the sequence into n elements, then at least one of them is already very small with respect to the supremum norm. And this is somehow the reason why the decomposition always fails. Okay, and this condition, which characterizes small LP spaces, is an F sigma delta condition. So it follows that the isometry class of small LP spaces is F sigma delta. Well, and the fact that it is F sigma delta complete is proved by, well, we construct a reduction of some known F sigma delta complete set into this isometric class. So it follows that this isometric class must be also F sigma delta complete. Well, and finally, the last theorem, which I will talk about, that is the isometric class of the space C0. It is also F sigma delta complete. And okay, the proof starts similarly. We again starts from the class L infinity 1 plus separable Banach spaces, which are usually called Lindenstrauss spaces or L1 preduals, because these are the spaces such that their dual is isometric to L1 of some measure mu. But again, the definition of these spaces is very similar to the previous one, and again it holds that the codes of these spaces form a G delta set. And now we found F sigma delta characterization of the space C0 among all such spaces. And this characterization is based on the Schlenk derivative. So it states that a space X is isometric to C0 among all these spaces, if and only if we start with the dual unit ball and we take the 2 epsilon Schlenk derivative of this dual unit ball, then we get a ball of radius 1 minus epsilon. So this is the characterization. And to show that this condition is an F sigma delta condition, we must prove something about the Borel complexity of the Schlenk derivative. And actually, we prove that the mapping, which takes a weak star compact subset of the dual space and maps it to its Schlenk derivative, is of Baire class 2. Yeah, so this finishes the proof. Well, actually, it finishes the proof of the fact that the set is F sigma delta. And again, to prove that it is F sigma delta complete, we find a reduction of a known F sigma delta complete set into this isometric class. Well, so this is everything I wanted to talk about. Let me just mention that this talk was based on these 2 papers. One of them is already published and the other is a preprint, but you can find it on arXiv. And thanks again for the opportunity to give this talk.
Well, thank you, Martin. That was beautiful. Okay, are there any questions or comments?
Hello, can I?
Yeah, go ahead.
Can I ask a question?
Mm-hmm.
Hi, thanks for the talk. This relation that you mentioned and that you use quite a lot, that the closure of the isometry class of the Banach separable Banach space are all the finitely represented spaces.
Mm-hmm.
Would there be some analogy for, let's say, crudely finitely represented, or would there be some possible application coupled with Ribet theorem? You know, when you have 2 uniformly homomorphic Banach spaces, then each one is crudely finitely represented in the other. Or did you think about something like this?
I don't remember much, but we definitely didn't think about it too much. Yes, I don't know. We have something more than this fact, but I think that everything we have is about finite representability only. But I don't remember. Sorry.
No problem. Yeah.
If I may speculate about this, I think that if you consider for every C, so you fix your X and you fix a C, and you look at the class of all spaces that are C isomorphic to X, then you take the closure of that and you take the union of that for all C's. That should be the class of Banach spaces that are crudely finitely representable in X.
Yeah. Yeah.
Just
sounds like a good guess. Yeah.
I believe we had some attempts in this direction, but we are not able to prove it. So we wanted to. I don't remember exactly as Martin said, but what you say is natural, but there was some problems. It's not so obvious, or at least it seems not to be, because okay, I would have to go into technical details, but.
Tony, did you mean that you want to look at uniform homomorphism classes of an X and whether that is coincide with this?
Or maybe you would need to control for the constant also of the core, because of course uniform homomorphism is really a core slip sheets equivalence. So maybe you would have to control the distortion of that, and then you would get then you would get the crude finite representation with the same constant. So I don't know. That was just you know,
Yeah.
keep the conversation going.
Any other questions, comments? Okay, if not, thanks again, Martin. That was really nice. Thanks for giving the talk.
Thank you.